Good morning, everyone. Welcome to day 4 of our R week for the Summer Research Methods Camp. We're going to start this morning not necessarily talking about models or how to fit models necessarily. We're going to talk about some different strategies for resampling your data, which then we will use for modeling this afternoon and tomorrow. So we will go ahead and get started. So let's go ahead and start by opening up the exercises for this set of slides. It's in your exercises folder as all the other ones have been, 10 resampling, and then go ahead and run the setup chunk, which should just be loading a few packages for us. All right, so we're going to talk about some unicorns some more. So bear with me. So if you Google unicorns, just Google like some images, you'll see a whole variety of things come up. So there's some books, there's some clothes, there's some shoes, all of these different things like you might find when you're Googling like unicorn photos. But you also see other things on these images as well, right? It's not just unicorns. And so as we're Googling through all of this, we might come up with a hypothesis that as the number of unicorns increases, so does the number of rainbows, right? So that is our hypothesis that we're now going to try and evaluate. And so we collect some data and we make this scatter plot that has the number of unicorns that we see on the x-axis and the number of rainbows that we see on the y-axis. And if we fit a line to this, we'd see that there's actually no relationship between unicorns and rainbows. But we are not actually gathering the entire population of images that contain unicorns and or rainbows, right? In reality, we're getting a sample. So we're just getting a few images, maybe like the first 50 that we see on Google or whatever the case may be. And we're going to try and estimate the relationship between rainbows and unicorns based on our sample of data. And so with this sample, again, we see pretty much no relationship, which is what we would hope if we have a random sample that's representing our population adequately. Our challenge then is making sure that our sample is representative and truly random and not biased. So sample bias can look like this. Maybe we just randomly happen to pick these images, and then we would estimate a negative relationship. So the more unicorns there are, the less rainbows we see. Alternatively, we could get a sample that looks like this. This doesn't look too bad necessarily, but we see a pretty strong positive relationship. And so our solution is going to be random sampling, at least random sampling of the data we have collected. So when we do a random sample, in theory, if we just randomly sample some points, we should get lines that are close to what the true population would give us. So here's an example of one random sample. Here's another random sample. Another random sample that looks a little bit like a negative relationship, but not too bad. And so as we keep doing this, we end up with sample variation, right? So there are all these different lines that we could draw based on which random sample from our population we select. And if you do this a ton of times, you'll get a ton of different lines. And you can see some of them do end up with a pretty strong negative or positive relationship, but the majority are in this darker region right here in the middle, showing almost no relationship. So we have another challenge, which is the variation in the sample. So if we select multiple random samples, how different are they? If we have a larger sample, there's going to be less variability because every large random sample we draw is going to be closer to the population. So there's less opportunity to vary between our random samples. So here's one random sample. We can make another one with, again, a large N and another and another. And when we put all those together, we see almost all of these lines show a very close to zero relationship. And so as we do bigger and bigger samples, we have less and less variability in our samples. So we get much tighter or lower uncertainty in our estimated relationship. But we don't have to constrain this to linear lines. Like we can do flexible models like we talked about yesterday. So here's one where we fit a polynomial model to this random data set. And if we draw another random sample, we get a new line. And again, you can see that the flexible models are much more influenced by the sample that we draw, especially if it's a lower sample size like these. But we end up with a bunch of different curves. And so here we can compare what we're getting from our linear models, which again are these pinkish purple lines in the back, compared to our flexible models, which again show a lot more variability, but are still kind of centered around this area of no relationship. All right, and so the good news for us is that we don't actually have to collect any more data to get the benefits of this resampling. And we don't have to sacrifice the fit of our model in order to be flexible. And so we're going to talk this morning about how we can use some sampling techniques on the data we collect to get good estimates of our parameters and our errors. All right, so one way we can do this is with bootstrap sampling. Has anyone heard of bootstrap sampling before or used it? Awesome, good. Okay, so bootstrap sampling says that we are going to take our data that we have collected and we're going to resample it with replacement several times, and we will fit a line to it each time. So here you can see just a few points. So that's our sample that we've collected, and we resample it. And when we do that, we say, okay, there are 10 rows. So I'm going to draw 10 cases, but I might draw row 2 twice. So here the blue dots represent the cases that were included in our bootstrap sample, and the size represents the number of times that case was included. So here, like this one, this case was drawn a couple times for our resample. This one was only drawn once. And so you can see that the size of the dots represents how many times each case was included. And these gray dots are cases that were not sampled when we did our bootstrap resampling. And so you can keep doing this on your same data set multiple times. So here is the same data, but with a new bootstrap sample. So you can see now there are different dots that are gray, so they were not included. There are different dots that are bigger, so they were included multiple times. And we can keep doing this with our bootstrap samples over and over again. And this doesn't require us to collect any additional data. It's our same sample every time. We're just resampling it with replacement to keep getting different variations of our data set that we collected. And when you put all these lines together, we again see a collection of lines that shows the variability in what we would expect this relationship to be given our sample that we collected. And so if we compare this, on the left, we have our entire population. So you see a lot of these gray dots. So this is if we collected many random samples, what our different lines would look like. And on the right, we have just one sample. So you see just a few gray dots here. So we only collected our one sample, but we bootstrap resampled that many times. So one sample, many bootstraps, and we can estimate, again, the variability in this relationship, or what we expect the relationship to be. So you can see that these look pretty similar, although the one sample does have a little less variability than we would get if we could collect multiple samples. And as you might expect, if we do a larger sample size, we reduce that variability. So again, on the left, we have the same case we looked at earlier, where we just have a larger n. So we take a lot of large random samples, compared to on the right, where we have one very large sample, but do many bootstraps on that. And there, these lines start to look even more similar to each other. Is this distinction between many samples and one sample, but many bootstraps making sense? Great, good. Okay. And so as we create these bootstrapped samples, we can start to estimate statistics and create distributions of different parameters that might be of interest to us. So for example, we can create many bootstrap samples, and in each of our samples, calculate the correlation, in this case, between the number of unicorns and the number of rainbows. And we'll get a distribution of what we expect that correlation to be, or where we think the correlation, the real correlation would be. Right. And so we get some measure of the uncertainty around the correlation as well. All right, and so our tool in R for doing this type of sampling is going to be the rsample package. This is going to do a whole lot of different resampling techniques for you. We're going to focus on two today and the rest of this week, and that's going to be bootstrap sampling, which we have been talking about so far. And then we're also going to talk about cross-validation and what that is and when it can be useful for us. And again, there is a chapter in the Tidy Modeling with R book that talks about different resampling techniques to evaluate your model performance. All right, and so the data we're going to use this morning for our resampling is the Palmer penguins data set. So this data contains information on 3 different species of penguins. And so these are chinstrap penguins, gentoo penguins, and Adelie penguins. And if you look at the penguins data, so if you've run your setup chunk in your notebook, you loaded the Palmer penguins package. And so if you type penguins in your console, you'll see this data pop up. And so you can see for each penguin, you have the species of penguin, the island where it was observed, the length of its bill, the depth of its bill, the flipper length, body mass, and then it also contains the sex of the penguin and the year that the observation comes from. So that's our data that we're looking at. Just in case you're interested in penguin anatomy, the bill length that we'll be talking about is from the tip of the bill to the base, and then the depth is from the top to the bottom. All right. So the bootstraps function is what's going to create bootstrap samples from a data set. So for example, if we wanted to make bootstrap samples of our penguins data, we would say we're going to bootstrap the penguins data and we tell it how many samples we want. So here we're specifying we want 25 bootstrap samples. And whenever you're doing this type of resampling, it's very important to set your seed. So this is a random seed that you're setting in R. And by setting the seed at 100 or whatever number you wanted to put in here, you're ensuring that every time you run this, if you run set seed first, you'll get the same bootstrap samples. All right, so since this is a random sampling process, you want to make sure that you always start in the same place. Otherwise, you'll run an analysis and then you'll go back and run it 6 months later and you'll get slightly different results because you're getting slightly different samples, right? So setting your seed ensures that you're always going to get the same results every time you come back to this analysis. And for us, setting the seed means that we should all get the same results if we're all running similar versions of R. All right. So now we're going to create some bootstrap samples. So I would like you all to use the bootstraps function to create 100 bootstrap samples of the penguins data, save that object as penguin boot, and then be sure to keep your set seed 100 so that hopefully we all have the same results. Okay, so it'll take a couple minutes to get those samples created. All right. So let's take a look at how we will do this. We've set our seed at 100. So if we all use 100, we should hopefully get the same results. And we're going to say penguin boot is going to be bootstraps of the penguins data. And we want 100 bootstraps. All right, and so if we run this and we look at penguin boot, what do we see? So we get a data frame back and we have a column called splits, which is a list. So we'll talk about what that means in just a second. And it says we have in each of these rows a split object. And then we also have an ID. So it says this is bootstrap 1, bootstrap 2, and you can see that we have 100 rows. So we have one row for each bootstrap resample that we requested. Okay, so let's talk a little bit about what this is actually showing us. So again, here's our output, and we want to know like what this list thing is that we've gotten back. So in our slides yesterday, we looked at this $ operator and said that that was how you could pull out a column from a data frame, right? So when we were getting our observed scores for calculating our RMSE yesterday, we had something like Stack Overflow test, $, the true remote status. That's how we got the observed values. And so here we're doing the same thing. We're pulling the splits column out of our Penguin boot data set. And then what's new is this bracket 1, which means just give me the first element of this column. And so it's going to return just this split object. And so we see that it is very unhelpfully just some numbers that says 344, 134, 334. And so the question is, what does that mean? All right, so let's talk about what a split object actually is. So again, we see these numbers. So the first number, that's going to be the size of the resampled data. And so it is the same as our total size, which is good. That's what we expect. If our total sample size is 344, we expect our resampled data to also have 344 cases. The second number is the size of the data that was not resampled. So remember, when we do bootstrap sampling, some cases are going to get selected multiple times. Some cases are going to not get selected at all. And so in this particular case, there were 134 cases that were not selected at all. So if you were thinking about this in a testing set, training set sort of scenario like we had yesterday, this resampled data would be your training set. And then the testing set would be the observations who are not included at all in your training set. So we have our training set, our testing set, and then the last number is just the total size of the data set, which again is 344. And so for bootstrap sampling, we would expect that this first number and last number are always going to be the same, because for bootstrap sampling, we're drawing the same size of data set with replacement. When we talk about cross-validation a little bit later, these numbers will be different. All right, so that is what our split object is telling us. That's what these numbers mean. And so from the split data, we can start to pull out the data that was actually resampled. So we can make a new object. This is kind of small, but it is that same. We're taking our Penguin boot data, the splits column, and again, that first element with the bracket 1 notation, and we're going to call that boot 1. And so if we look at boot 1, we see again that 344, 134, 334, and it's telling us now that that's the analysis, the assessment, and the total. And so if we run the analysis function, so we can say analysis for boot 1, it'll return the analysis data. And so this is going to be similar to our testing and training functions that we learned yesterday, except analysis and our next function, assessment, are used on resampling methods, whereas the training and testing was used for that initial split function. And so that is like a little bit confusing. Why would we not just use the same functions? Tomorrow, we're going to do a case study that kind of ties together all of the modeling stuff that we've learned yesterday, today, and tomorrow. And so hopefully that will be a little more clear on how all of the pieces fit together and when you're using each function. But for right now, just know that when we're doing bootstrap sampling or cross-validation, we're going to use the analysis function to pull out the actual data that was resampled. And we can use the assessment function to pull out the rows that were not sampled. So here, our assessment function is going to return a data frame that has 134 rows because there were 134 cases that were not sampled as part of the bootstrap resampling. All right, so a quick quiz. If we look at our Penguin boot data, we can see that for each of these splits, there are 134 or 344 cases always in this first one. That's your analysis set. And then the second number here is always changing, right? So the question then, and feel free to throw it in the chat or unmute yourself, or if we get to a minute, then I will just give you the answer. Why is the assessment set a different size for every resample? Does anyone have any thoughts? So remember, when we do our bootstrap resampling, every time we draw a sample, we're sampling a different set of rows. And so sometimes rows will be excluded. They won't be sampled at all. Sometimes rows will be sampled multiple times. And so this randomness means that we won't always have the same number of rows that get excluded. So for example, here we had 134 rows that did not get sampled at all. In our second set, we saw that there were 126 that did not get sampled at all. So because there were more that did not get selected in this first set, what we then can infer is that more rows were selected multiple times in this one. Right, so we're always going to sample 344 rows, but with replacement, which means there will be varying number of rows that are not included. Does that make sense why we're getting different numbers for the second value? Awesome, good. All right, so let's talk about how to start using these resamples. So in R, we can estimate a correlation using the core function. This is part of base R. It just comes with R as part of the default installation. So again, we can look at our boot one, which we'll call our penguin, our first resample. So that splits column from penguin, again, bracket, bracket one to get that first resample. Call that boot one. And we use the analysis set to get those 344 rows that were resampled. And we'll call this boot sample. And so boot sample is going to be a data frame that looks just like our penguins data, but resampled. And so we can use the core function, and we say we want to look at the correlation between the bill length and the bill depth. And if you try this, you'll get NA, just missing, which is not very helpful for us. What's happening is that we have some missing data. And so by default, this core function, if there's any missing data, it will give you a missing value back. So it won't compute a correlation, but we can force it to. So we can tell it which data to use. And so we say use only complete observations. So it'll only use cases where both the bill length and the bill depth are present. So another way you might have heard of this is list-wise deletion. So it's going to just delete any row that doesn't have data on both of these variables. And we see that we get a correlation of about -0.12 for the correlation between bill length and bill depth. All right, so now we're going to try this. So I've provided some template code that I would like you all to complete. So what we want to do is take the 5th bootstrap resample and calculate the correlation between the bill length and the bill depth. All right, so we'll take a few minutes and then look at what that correlation is. I guess it's helpful if I unmute myself. So the way that we do this is we say from our penguin boot data, our splits, we wanted the 5th resample. So here we do bracket bracket 5 to get that 5th element. I call that boot 5 to get our sample. We then do the analysis, get the analysis data from boot 5. And then we can estimate our correlation in the same way with that boot sample. So the bill length and the bill depth with using complete observations. And here I get a correlation of a negative 0.25-ish. Did everyone else get that correlation or something similar if our bootstrap samples were a little bit different? Thumbs up, good. Awesome, yeah. So again, we may not get exactly the same correlation if our versions are a little bit different or if we use different seeds, but something should be right around there. All right, and so we've looked at how we can get a correlation for a single sample, but we got 100 bootstrap samples, right? And doing this 100 times sounds like a nightmare to me, like not anything that I want any part of, at least manually. Like I don't want to have to type this 100 times or copy and paste it and try and like change this number. Like I will have a typo, something will go wrong and I will not get the right answer. So we're going to talk about how we can automate this process to go through a bunch of resamples at once. And for this, we're going to use the purr package. And purr is actually part of the tidyverse, not tidy models. It's used for iteration. And so there is a chapter in R for Data Science on iteration that talks about the purr package. We're just going to very briefly do a high-level overview of purr to make it do what we need for our purposes. But there's a lot you can do to automate tasks in R with purr. And so if you go back to our applied data science diagram, this is very much in the programming piece, right? So it's not necessarily part of any analysis pipeline, but purr is going to make a lot of these steps much easier if you're able to automate through a lot of things very quickly. So purr's main function is called map, and there are some quote unquote friend functions that we'll look at in a second, which are just different versions of the map function. And what map is going to do is it is going to apply some function to every element of a list. And so for us, that list is going to be our bootstrap resamples. So we have 100 of them, and we want to do the exact same thing to all 100 of our samples. And the friends of map are these map underscore something. So there's map underscore CHR, map underscore DBL, and these are different types of outputs you would expect. So if you're expecting to get back a character, you would use map CHR for a character string. If you're expecting to get back a number, like we are, we're going to be getting correlations back, and we would use map double. So again, double are those decimal point numbers. There's map int for integer if you're expecting a whole number back. Map LGL is map logical if you're expecting to get a true false back. There's map DF, which is map data frame. So if you are doing some analysis that's going to give you a data frame back, you can use map DF, or you can just use the general map, and that will give you a list back. So no particular assumptions about what kind of output you'll be getting back. All right, so to build our map, we first give it the list that we are wanting to iterate over. And so that's our splits from our penguin boot data frame. And then we have to give it a function. We have to tell it what we want to do. But as you are maybe realizing, there is no function built into R that does what we want. Like there is a function that pulls out the analysis data. There is a function that calculates the correlation, but there's not a function that does both of those together. And so in order to do this, we're going to have to create our own function. So we need a function that's going to take in a split object. It will pull out the analysis set for us, and then it will calculate the correlation. All right, and so we're going to look at how we can write our own function to do this. So the first step to create a function is to write the code that you need to happen. And so this is basically our code from earlier. We know that our function is going to take in a split object. And so we give it, we can say, okay, we know what we want to do is get the analysis of our split. And so earlier when we had our code, I go back a few slides, we were calling this, we were getting the analysis of boot 5 or boot 1. But what we're saying now is this is basically going to be every split. Like we're going to be feeding every split into this function. So we need something a little bit more generic. So we'll say we just want to pull the analysis of whatever split comes in here. We'll call that boot sample and then calculate the correlation between bill length and bill depth from that boot sample object, which again is the analysis set of whatever split we send in. And so once we have this code, we just wrap it inside the function, right? So there is a function in R called function, and that is going to create a new function. So say function again. So we are going to call our function penguin core. So it's going to calculate the correlation of the penguin data for us. And so we say, okay, penguin core is going to be a function, and it is going to take a split object. And so we then do curly braces and put our code inside the curly braces. So when we do penguin core, we'll give it a split, and then R will execute this code on whatever split object we give it. And penguin core is just the name of the function, so we can call that anything we want. I could call it Jake's function, or like bill correlation, since we're looking at bill length and bill depth. It can be whatever you want it to be. And then the last step, we should verify that it works, right? So if we do our first bootstrap resample again, so we do our penguin boot, we could get out the first resample and we call that boot 1, get the analysis set, calculate our correlation, we get the negative 0.12 that we saw earlier, right? So this is the value we're expecting to get. And then if we do our penguin core for boot 1, which again is just our first split object, we get the same value, right? So our function that we wrote is working as we would expect. So does this make sense, how we wrote our function and now we have a single function that will do all of these different pieces at once for us? Awesome, great. Okay, so now we can finish building our map function, right? So we have our list that we want to iterate over. Again, the splits from our penguin boot data. And we tell it what function we want to use. And that's the penguin core function that we just created. And so when we run this, when we run this line of code, we now get all of our correlations back. So again, there's that same correlation we saw for the first bootstrap resample. If we look at the fifth bootstrap resample, which we did in our previous exercise, we see that negative 0.24. You should see here, if you run this, whatever value you got for your fifth bootstrap resample. And so that's like our very, not necessarily easy, but we now have a way that we can iterate quickly over all of our bootstrap samples without having to manually calculate each correlation. All right. And we can also use map within mutate, right? So we can take our penguin boot data and say, okay, we want to add a new column that contains the correlation. So we're going to use mutate, and our correlation is going to be the result of this map function. Right, so map's going to return 100 correlations, and so those 100 values will go in this new core variable. So again, we're going to map over our splits. So take our splits column, we're going to map over that, and we're going to map the penguin core to each row of this data. And so then we have a new column called core, which has all of our correlations. Right, but this is not pretty to look at. So it gave us a list back. And so it just tells us that each row has one single double. So one number in each of these. And so the reason we're getting a list back is because we're just using the normal map function. So it's not making any assumptions about what type of output this penguin core is giving back to us. Right, but we can make this better. So if we use map double, we say, okay, we're expecting to get a decimal point number back. So now our core variable is a double. It's just a normal numeric. And so we have a column that's just all of the individual correlations. And so what'll happen if you specify map double and your function doesn't return a decimal number, you'll get an error. So it'll say, hey, we were expecting a double. It didn't give us a double, like something's wrong here. So not only does using these functions like make your data a little bit nicer to work with and look at, it's also very good just in terms of like data quality, data management. Like if you're expecting a double, you should use this so that way if you don't get that, you know early. So it's better to find the errors early and fix them than to find it 4 or 5 steps down your analysis pipeline and then try and figure out what went wrong. So highly recommend if you are expecting a certain type of output, use that map function. All right. So let's play with this a little bit. So what I would like you all to do is use the map functions we've talked about and mutate to calculate the correlation between bill length and bill depth. So you're going to have to write a function that will calculate the correlation from the analysis set of a split. You'll apply that function to every bootstrap sample using mutate and the mapping function. And then what I would like you to do is use ggplot to make a histogram of those correlations that you've calculated. So let's take a few minutes and work on that, and then we'll come look at those correlation distributions. All right, so let us look at how we can build this up. All right, so the first thing we need to do is write our function. So it's going to take in a split object. And from there, we need to pull out the analysis set of data from our split, and we'll call that boot sample is analysis of our split. And then we want to calculate the correlation of the bill length and the bill depth. And we'll have to use only the complete observations. All right, and now that we have that function, we can calculate our correlations. So if we start with our penguin boot and we mutate a new variable called correlation, we're going to map double the splits from our penguin boot data with the penguin core function. And so if we run this, we should get our correlations, which we do. And so then we can just pipe this directly into ggplot. So we're going to make a histogram, which means we need an X variable. So we're going to put our correlations on the X axis. And the histogram only requires that X aesthetic. So we can then just say geom histogram. And if we run that, we see our histogram, so the distribution of all the correlations from our 100 bootstrap samples. And we get a little warning that says it's using 30 bins by default, and we should pick a better bin width. If we want to do that, we can specify the bin width that we want. So maybe 0.05, I'm just guessing. Okay, that was a bad guess. We have really thick bars now. So maybe we want to do something like 0.02. So you can play around with your bin width to get a histogram that makes sense. Was everyone able to create a histogram of their correlations? All right. So maybe need just a little bit more time. So the thing about histograms, I'll just keep talking about bin width. They can kind of tell different stories depending on which bin width you use. So here, I might want to think more carefully about what ranges of correlations make sense. So we don't want too small of a bin width because then we get something that looks very jaggedy like this. Like this is not anything useful to look at. But again, my original guess of 0.05, like this probably isn't too helpful either. Like we're really not seeing the variability here. So I don't know, maybe like point. This seems reasonable-ish to me, but to each their own. And it's really easy to modify this. So for example, if we wanted to look at the correlation between bill length and flipper length, we could just easily change our penguin core function to be flipper length, if that's actually the name of that variable. Penguins, yes, flipper length. And so now that we've changed our function, if we run this, we now get the correlations between the bill length and the flipper length. And so you can see those are around 0.65. All right. All right. So again, we have our function, our code to create the histograms and calculate the correlations, and then our final plot. All right. So we can also summarize across our bootstraps. So for example, after we mutate and calculate all of our individual correlations, we might want to know, okay, what's the average correlation across all of our bootstraps? Well, we can do that with the summarize function. We can calculate the average core as just the mean of that correlation variable. And we see that there's an average correlation between bill length and bill depth of negative 0.24 about. And we can add additional summaries if we want to do that. So we can create a 95% confidence interval for each one. So we can say our 95% confidence interval, this quantile function will create, we'll let you know what value is it different quantiles or percentiles. So here we say we want if we want the middle 95%, that means we need to go from the 2.5% to the 97.5%. That'll give us the middle 95% of the distribution. So give us the 2.5 and the 97.5 percentile of the core variable. Again, it's the quantile function that will do that for you. And then just so we know what is what, we give it some labels. So we say we're going to make another quantile variable that has the values of 0.025 and 0.975. And so we can see that the lower range of our correlation is negative 0.32, and the upper range is negative 0.14. So that's our 95% interval of our bootstrap samples for where we think the correlation is between bill length and bill depth. All right, and so we can make a plot of this. So we have bill length and bill depth, and we see our negative correlation of 0.24, so that negative relationship. And now here's my just constant warning to always look at your data. So if you actually do this by penguin species, you see that it's actually a positive correlation between bill length and bill depth within each species. So ranging from 0.39 to 0.65 or 0.64. A positive relationship between bill length and bill depth. So this is an example of Simpson's paradox, where each group has a positive correlation, but if you collapse across groups, you find a negative correlation. So no amount of resampling or fancy statistics will get you around this. So it's always important to be looking at your data and make sure that you are understanding what's going on. So even though bootstrap resampling is like super helpful and like a really efficient way to analyze your data, it's not going to be able to catch issues like this for you. All right, so we are coming up on our break for the morning. We're ready to switch over to talking about cross-validation. So we will go ahead and take a 15-minute break now. So we're at 10:08. Just for my math, we will call it 10:10. So we will come back at 10:25 a.m. Central Time, and we'll talk about cross-validation. All right, go ahead and give me a thumbs up or let me know in the chat that you're back. Great. All right. So we are going to transition now to another form of resampling known as cross-validation. And so we're going to start by kind of repeating some of the stuff that we were doing at the end of the day yesterday. So what I want you all to do is use the initial split function we talked about. So try and remember what we were all doing late on a Wednesday afternoon to create a training and a testing set of the penguins data. And then we're going to write a parsnip specification to fit a linear regression model. And when we want to predict bill length from flipper length, and then use the testing data to calculate the root mean squared error, the RMSE. Right, so let's take a few minutes to do that, and then we'll come back and make sure that we are all still remembering what we did yesterday. All right, so let's refresh ourselves on how we can fit one of these models. All right, so the first thing we want to do is create a split object from our penguins data. So I'll call this penguin split, and I'll use the initial split function to create a split of that penguins data. And then I need the testing and the training set. So I'll call this penguin train is the training. And then the penguin test will be the testing. Okay. The next thing I need to do is specify my linear model. So I'll call this LM spec. And this is a linear regression model that we're fitting. I'm going to set the engine to be the LM function. And I don't have to set the mode here, but I will anyway, just to be clear that we're doing a regression model. So then I can fit the model. So I'm going to fit that LM spec object. And we want to predict the bill length from the flipper length. So we're going to predict bill length in millimeters. And our predictor variable is going to be flipper length. And the data we're going to use to train this model is our penguin train data. And then our last step is to get our predictions. So I'll call these LM preds. And we want to predict from our fitted model. So from this LM model, I'm going to make predictions, and our new data is going to be our testing data. And we will add to that a column that has the observed values of bill length. Okay. And so once we have our predicted values, we can calculate our RMSE. From our predicted values, truth is going to be the truth column, and the estimate is that dot pred column. All right, and so if I run all of this, I get an RMSE of 3.84-ish. And we should all have something similar to that. It won't be exactly the same because, again, this initial split function is randomly partitioning our data into a test and a train set. So all of our training and testing sets are going to be a little bit different. So we'll have a little bit different coefficients here, which will lead to a little bit different predicted values and different RMSEs. But it should be somewhere around there. So is everyone able to get an RMSE from their linear model and remember what we were doing all of 18 hours ago? All right. All right, and so we kind of talked about this, but what would happen if we did this process again? So take a couple minutes and just run that same code chunk a few times. And so each time you'll get a different testing and training set. You should get a different RMSE. So take a couple minutes, rerun that code chunk, and just verify that either one, you're getting the same values or you're getting different values. All right, so hopefully if you run this a few times, you see that each time you get a slightly different RMSE. So here I've run it 6 different times and I get 6 different values, right? And so why is that estimate different, right? And we talked about this a little bit already. So every time you run that code, the initial split function is partitioning your data in a slightly different way. Like the 75% that are going into the training set is a different 75% every time. So you're going to get different coefficient values. There are different cases that are being used for predicted values. And so all of that together is going to give you a different error estimate. And so what's happening, if we want to visualize it, is we're starting with our full data set. And in our first iteration, these yellow blocks here represent our training set and the green dots represent the testing set. And so every time we do this, we're getting slightly different variations on what's in the training set and what's in the testing set. And so every time we do this, we get a slightly different sample. And from that, we're calculating an RMSE. And so we do this over and over again for every different sample. And then what we could do at the end, after we do this many times, is calculate an average RMSE. And so then that would give us a better estimate, hopefully, of what the actual error of our model is going to be. And just as an example, from the previous values that I showed you, if I did our previous model 10 times, these are the 10 RMSE values that I got, and that would give us an average RMSE for our penguin model of 4.2. Right? And so in the chat, or just think about it for a minute, which do you think is going to be more accurate? Is it going to be the mean of all of these, or is it going to be the best of all of these, which would be, I think 3.65 is the best RMSE we got. So we have 1 vote for mean value. 2 votes, yes. Yeah, so the mean is going to be a much more accurate evaluation than just picking the best value. And so how can we do this? Like, so this is one way that we're not going to go into detail about. It's a lot of code where we are fitting our model however many times we want to do it. So here, I'm just creating an empty vector of length 10. And so it's going to go through this for loop 10 times. It's going to pull out the test and training set, fit the model, calculate the RMSE. And so this is perfectly valid R code. It will work, but it's not super clear what's happening in here. And so we're going to use a better way, or at least a cleaner way, from the rsample package. And that's going to be vfold cross-validation. So there's a vfold CV package, or not package, function, which will do this for us. And so what this function is going to do is it's going to create analysis and assessment sets from the data we provide it in however many folds or iterations we specify. So a lot of times you'll see a 10-fold cross-validation. And so over 10 different samples, it will partition the testing and the training sets. And so when we use vfold cross-validation, or you might hear this also as k-fold cross-validation, it's all the same. How many times does an observation or a row appear in the assessment set? right? And if you look at this, and if you like look down all the columns and across the rows, you'll see that each observation appears only once in the assessment set, right? So this first observation is in the assessment set for fold 9 and never anywhere else. The second observation is in the assessment set for fold 7, but never any else. So the v-fold cross-validation not only is creating these like testing and training sets for us, but it's also ensuring that each observation is equally represented in the training and the testing set, right? So the second observation isn't always in the assessment set or always in the training set. It gets evenly distributed. Each observation will be in a training set and a testing set an equal amount of times. And so if we sort that last table, you can see that each observation appears only once in the assessment set. All right. So if we use 10 folds, what percentage of our data is going to end up in the training set and what percentage is going to end up in the testing set? So take a minute to think about that. Put your answers in the chat. And then we'll talk about what we think the answer is going to be. All right, does anyone have any guesses? So if we are doing 10 folds, that means that in each fold, 90% of our data is going to be in the training set and 10% is going to be in the testing set. So if we go back to our graphic here, if each observation is only going to be in the assessment set once, that means if we have 10 assessment sets, then 10% have to be in each one. So if we look across this, if you were to count it, there's 20 cells here. And so 2 of them, 10% are in the assessment set for each fold. And so if we were doing, for example, a 5-fold cross-validation, then you'd have 80% in the training and 20% in the testing. And so if you have 5 folds, then 1/5 will be in the testing set. All right, so let's make a v-fold cross-validation resample set. Take a minute, run this code, and see what it gives back to you. Okay, so hopefully if you're able to run that code, you get something back that looks like this. So this looks like our Bootstrap output. It's going to give us 10 rows, one for each fold, and we see a split object. So here again, we see the number of cases that are in our analysis set and the number of cases that are in our assessment set. And so unlike in Bootstrap sampling, this is not our total sample size anymore. It's not 344. And that's because we're not sampling with replacement. Here we are very intentionally partitioning our data so that some observations are in the training set and some observations are in the testing set. And so we have just about the same number of cases that are always in the training and just about the same that are in the testing. And these two numbers will always add up to 344, our total sample size. All right. And so how does this help us? So there's a function in the Tidy Models ecosystem called fit resamples. And that's going to allow us to fit models to multiple resamples. All right, so the fit, and this should be fit resamples, not fit samples. The fit resamples function is going to train and test a model with cross-validation. And you don't have to use vfold CV in order to use the fit resamples function. You could use Bootstrap sampling here, but the key is that you have to be fitting a model specification. So we could not have used this in our last example for correlations because we're not fitting a model necessarily there. Right? But with fit resamples, we can say, okay, we want to take that linear model specification and this formula, and we want to fit that to all of the resamples in our CV folds object, right? And so our CV folds was this data frame of all of our penguin splits. And so if we were to run this code, we get some output that looks like this. It tells us it's our resampling results. And so we have the split, the ID of our split, so which fold number. And we now have another column called metrics. And so this is going to have the metrics for each of these 10 models that got run. And there's another function called collect metrics, which is going to create a nice summary of that for us. So by default, a regression model is going to use the RMSE and the R² values for collect metrics. So if we do this, we can see that across all 10 of our folds, so it tells us in this in column how many observations it's using, which is 10 for our 10 folds, the average RMSE, and the average R² of our model. If you want to see all of the values individually, you can tell collect metrics summarize equals false. And then you'll get for fold 1, the RMSE and the R², and same for fold 2, RMSE, R², fold 3, etc. So by default, it will summarize and give you the overall value, but you can get the metrics for each individual fold as well. And so this makes it really easy to fit a parsnip model specification to however many resamples you have. And we can change the default metrics that get provided. So in the fit resamples functions, we saw the metric set function yesterday briefly, but we can say when we call fit resamples, the metrics that we want are just the R squared. And so then when we collect metrics, we'll just get the R squared and not the RMSE. So you can specify here any metrics that you are particularly interested in. All right. So let's try this. I've included here the model fitting code that we used earlier. And I want you all to modify this code to estimate our model on each of the folds and then calculate the average RMSE for our penguin model. And so we'll take a few minutes and then we'll come back and look at the answer. All right. So let's look at this. First, I'll get my CV folds. All right, so how are we going to edit this code? First, instead of fit, we need to use fit resamples. We keep our model specification the same. Our formula is staying the same. But now instead of specifying the data as penguins, we want to use some resamples. And for those, we're going to use the CV folds. And because the question asks about the RMSE and nothing else, I'm going to change the default metrics so that I only get the RMSE. And so if I fit that, I'll get, again, this data frame that has our splits and the metrics. And to get the average RMSE, I can collect metrics. And this will show me an average RMSE of 4.09. Did everyone get something similar to that, or was able to run this code, get it to run with the resampled objects? All right. So let's look at how we can use this to compare different models. What I want you to do is to use fit resamples and the CV folds to estimate two different models that predict bill length. So in the first model, we want to predict bill length from the flipper length, like we have been doing so far. And in the second model, we want to predict bill length from the combination of the penguin species and the penguin sex. Okay, so fit both of those models and then compare the performance of each. Which one do we think is doing a better job of predicting the bill length? All right, so let's look at how we can fit these two models and compare them. So our first model is going to be the same one that we just fit, this bill length predicted by flipper length. So I'll just copy this code down here. Right. And our second model, we're going to do the exact same thing, just with a different formula. So here we want to predict bill length from the species variable and the sex variable. And so if we run this chunk of code, it'll estimate all of these models. And we can see that our first model had a mean RMSE of about 0.4 or 4.1, and our second model an RMSE of 2.3. So the second model is doing a better job of predicting bill length. So species and sex together are a better predictor of bill length than just flipper length is. Was everyone able to fit these two models and come to a similar conclusion? Great. All right. All right, so here's a question to think about. So in that last example, we used the same set of cross-validation splits to compare each model, right? So even though we had two different formulas, we used that same CV folds for each. And so the question is, why do we do that? Why is that a good idea, or is it a good idea? So I think it's a good idea. And the reason is that it's an apples to apples comparison, right? So if we had a different set of folds for our second object, or for our second model, just by random chance, we might have two outliers in our data that both get put in a testing set in one set of the folds. And so that's going to skew the results. And so by using the same set of folds for all of your model comparisons, you make this apples to apples comparison, which is going to be good. So next question to think about, drop your answer in the chat or just think about it. When we're doing cross-validation to measure the accuracy of our model, is it looking at just the accuracy of our model or the entire modeling workflow that we have? All right, we have one vote for workflow, and I agree. It's your entire workflow. So if you are doing, can we elaborate on the question? Yes. So when we are fitting our model, we are not, here we've been focused kind of just on the model fitting aspect of it. But one of the things that we're going to start looking at is what happens before we fit the model. So here our data is kind of clean, but if we were doing any sort of feature engineering, or maybe we were calculating some additional variables from our data, all of those calculations then are part of the modeling workflow. So if we are calculating additional data for our penguin's data, and those aren't good measures, but we put them into our model, the CV fold cross-validation, it's not going to make up for that. We still have to give it good data in order to get good metrics out. Right, so just like we saw Simpson's paradox earlier with the bootstrap samples. Just doing this resampling, even though it's powerful and can be really helpful for evaluating your model, it's not a like idealized solution. Like it's not going to just magically solve all your problems for you. We still have to think about everything that goes into the model besides just the model fitting process. All right, and we're going to talk more about what those steps are either tomorrow morning or maybe this afternoon if we move quickly. The next couple of slide decks are a little short, so we might actually start feature engineering this afternoon instead of tomorrow morning. And we'll talk more about what else is going into your modeling workflow besides just the actual model. Right, so there are other types of cross-validation. So we've talked about one, which is v-fold cross-validation. So that's going to take a percentage of your data and partition it out for each fold. The extreme version of this is leave one out cross-validation. And so in this case, one single observation will be held out every time. So if you have 100 rows in your data set, then it will have essentially 100 folds where each fold has 99 observations in the training set and 1 observation in the testing set. So it is kind of the most extreme version of v-fold cross-validation. There's Monte Carlo cross-validation, also called like random cross-validation. And so this is test sets sampled without replacement. And so this is going to be similar to cross-validation or to v-fold cross-validation, but it's not as strict in how the data is partitioned. So for example, when you use Monte Carlo cross-validation, some observations will end up in the test set multiple times. So you can see like this second to last observation is here 3 times in the assessment set. This first observation appears only once in the assessment set. So they're always the same size. If you go across the rows, there will always be 5 blue boxes, but it's not as strict as the v-fold cross-validation in ensuring that each observation appears equally in the test set. And then there's bootstraps. So we used bootstrap sampling not for model comparisons earlier, but you could create bootstrap samples and use fit resamples on those bootstraps. And these are test sets sampled with replacement, whereas the Monte Carlo was without replacement. All right, so does anyone have any questions about resampling methods before we move on to our next modeling topic? No? Okay. So let me pull up the next set of slides. All right, so we are now going to talk about ensembling, model ensembling. All right, so why don't we go ahead and start by opening up the notebook for this section of slides in your exercises folder. It's called ensembling. And we'll run the setup chunk and I will do the same. All right. All right, so let's refresh ourselves on our modeling kind of flow. So we start with our data. We split it into some quote unquote old data and new data. We use the old data and some model, like a linear regression model, to create a trained model, which we then combine with our new data to get predictions and then metrics of our model's performance. And within the Tidy Models ecosystem, so far we've looked at 3 main packages for doing this. We have the rsample package, which is used for the data splitting. We have the parsnip package, which is used for defining our models. And then the yardstick is used for creating metrics. All right, so we've seen this before, but just a refresher, when we're specifying a model with parsnip, we first have to pick our model, we set our engine, and then if necessary, we set the mode. And so let's go back to a classification tree. So we can define a classification tree in parsnip with the decision tree function. We'll set the engine to be the rpart package. And we're doing a classification tree. So we'll set the mode to classification. And so we'll start in our notebook with a very vanilla, and I say that because it's just the default arguments, model specification. And so this vanilla tree spec is also in your R Markdown document. And so all we've done is use the default arguments for the decision tree. We've set the engine to rpart and set the mode to classification. And so what I would like you to do, you all to do now, is fill in the blanks in the code to return the accuracy and then the area under the ROC curve for this model. All right, so let's take a couple minutes, run this code, and see what we come back with. All right, so let's fit this model. All right, so we have our vanilla tree specification, and we're creating some folds with vfold CV. And again, this is going back to the Stack Overflow data that we were looking at yesterday. I should have mentioned that earlier. So again, we're predicting whether one of these developers is working remotely or not. All right, and so because we're using the folds, we're going to use a fit resamples. The model specification that we want to fit is this vanilla tree spec. The formula that we specified here is remote and then this tilde and period. So if you remember, the period means we're just predicting remote from every other variable in our data set. And the resamples that we're going to use are this SO folds. And then once we fit those models, we want to collect the metrics to see how they perform. All right, so if we run this, we can see that our just kind of plain vanilla decision tree specification has an accuracy of 0.64 and an area under the ROC curve of 0.66 about. So not great, but it's okay. We're doing better than chance with our predictions. Was everyone able to fit their decision tree? Thumbs up, good. All right. So the decision tree comes with some default arguments, and we can look at those with the args function. So for example, if we do args for decision tree, we can see that it has a few that we are not specifying. So it has a mode, which by default is set to unknown, which is why we have to set the mode for this type of model. There's also these other arguments. There's this cost complexity, there's a tree depth, and a min-in that are also arguments to this decision tree that we're just kind of accepting the defaults on right now. Right? And so here we can see we can specify those if we want to. So we could set a tree depth, we could set a min-in and a cost complexity. We're going to talk about what each of these are. And again, this works for either regression or classification. And so again, we'll talk about what the max tree depth are and the smallest node allowed. And then just a note that the cost complexity is between 0 and 0.1. But we'll talk more about what each of these means specifically for a decision tree. There's also a set args function, so we can change the arguments for a parsnip model specification. So we could take our specification and then add a set args, a tree depth of 3, and then that will give us a model specification with the tree depth of 3. Or we could define that in our original call to the decision tree model. Either one is going to work exactly the same. So just like we could set the mode up here or use the set mode function, we can set these other arguments up here as well, or use the set args function. So let's talk a little bit more about what each of these mean. So tree depth is the maximum kind of depth that our tree can go, which is not helpful. I just defined the term with the names in the term. But if you think about the images of the decision trees we saw yesterday, there was kind of that root decision at the top, and then it kind of like fanned out as a triangle, right? So we kept like branching and making more and more decisions, more and more questions. And the tree depth argument is going to control like how wide you let that base of your tree get, right? So how many branches are you going to let it make? And that's the tree depth. And so we can set the maximum tree depth in order to force the decision tree to stop early, right? And this can prevent overfitting. Like you can imagine that if we just let a tree keep going and going and going for as long as it wants, eventually it's going to very much overfit the data, right? Because it'll be able to find eventually like unique nodes where like everyone has like the specific set of covariate values. And so if we set the tree depth at 30, then we say, okay, we're not going to let this branch more than 30 times. And so as an example, we can see that as we let the number of splits get higher and higher, our error rate, right, like our RMSE or our accuracy, like I guess this would be the inverse of the accuracy because accuracy is good and error is bad. Our error rate is going down and down and down. Right? And we're going to see a similar thing with cost complexity, and we'll talk about in a second. But what we see, as you might expect, is that as our error rate is going down in our training data, it kind of levels off with our testing data and actually starts to go up a little bit. So we're overfitting the data when we let these values kind of go to their extremes. Min-in is similar. So this is setting the minimum size to split at any node. And this is another early stopping method. So if you think about the decision tree again, we've like asked some questions, and each time we branch, and at each node, there's a set number of observations that have followed that path along the tree so far. And what the min-in argument is saying is, all right, if we set the min-in to 20, then if there are 20 or fewer observations at this particular node, we're not going to split it anymore. Like that's it. We're terminating this path on the tree. And so again, this can be used to prevent overfitting. So pop quiz, go ahead and think about this and drop your answer in the chat. What value of min-in would lead to the most overfit tree? Yes, exactly. Min-in of 1 is going to give you the most overfit tree, because that's going to, if you had a min-in of 1, basically every observation gets to be its own terminating node. And so you're going to get very specific about each path on the tree. So you'll be very overfit. All right, so to recap on the two that we've talked about so far, for tree depth, a high tree depth is going to result in overfitting, and a low min-in is going to result in overfitting. And you can see the default values for those are 30 and 20. So if you want to prevent overfitting, you can lower your tree depth and raise your min-in. All right, so cost complexity was the last argument for a decision tree to talk about. And so this is going to add a penalty for the complexity of your trees. Like the more complex your tree is, the more penalty is going to get applied. And so this is a little more abstract than the other two methods. But this is a way to kind of prune a tree, keep it from getting too complex, and therefore can prevent overfitting. Basically, it's going to drive your model toward a more parsimonious tree. And so we can specify that in the same way with the set args function. And values of the cost complexity that are closer to 0 are going to result in larger, more complex trees, and a higher penalty will be smaller, more parsimonious trees. So again, we can see with cost complexity on the x-axis here, as cost complexity goes to 0 and our trees are allowed to be larger and more complex, the error rate for our training data goes down, but the error rate for our testing data starts to increase. So if we return to our bonsai metaphor from yesterday, in order to properly care for your bonsai tree, you need a small pot and strong shears. And for our decision trees, these are going to be early stopping and pruning. And so early stopping is going to be the tree depth and the min in, and the pruning is the cost complexity. Right. So a high tree depth will result in overfitting, and a low min in and a low cost complexity will result in overfitting. Right. And if you're interested in exactly how this is working in the RPart package, there's a link here. But again, we don't need to worry about that too much because parsnip is going to take care of a lot of this for us. All right, so instead of our vanilla tree that uses the default arguments, we want to create a new classification tree, and we're going to call this a big tree spec. So this is going to be a much larger, more complex tree. We want to set the cost complexity to 0 and the minimum number of data points in a node that gets split to be 1. All right, so make that specification and fit that model, and then compare the metrics of our big tree to the vanilla tree, and which one is going to predict the test set better. All right, so let's take a few minutes to work on this one. All right, so let's create this big tree model. All right, so I want to do a big tree spec is what I'll call it. And this is going to be a decision tree, but we want to, the minimum number of data points in a node to split is 1. So that's going to be min n equals 1. And we said we wanted the cost complexity to be equal to 0. And then we'll continue to use our part for our engine. And we'll set the mode to be classification. And then I'll set a random seed so that I'll always get the same decision tree out of this. So I'll call this a big decision tree model. And I want to fit my resamples. The model specification I'm going to use is the big tree spec. The formula will be the same, predicting the remote status from all other variables. And the resamples that I'm going to use are the same Stack Overflow folds. And then once my model is fit, I can collect the metrics. All right, so if I run this, it will fit the big decision tree model, collect the metrics, and I see that I have an accuracy of 0.59 and also an area under the curve of 0.59. Was everyone able to get something similar and estimate this bigger tree model? All right, and we can compare this to our vanilla decision tree specification. So if we look at our metrics, here our vanilla model had an accuracy of 0.64 and an area under the curve of 0.66 for our testing set. And so we can see that we are overfitting with our big tree because our performance metrics are going down in the test set. Right, so we're not doing as well of a job because our tree is so big and complex that it's overfit to our training data. All right, and so decision trees are a really powerful model, but they're also very finicky. So for example, they're very model dependent. So if you have even just slightly different samples, you can get very different decision trees, right? And even if you have a different random seed for the same sample, you could get a slightly different decision tree. And so the question is, how can we deal with this sort of model in a like robust and reproducible way? And so for this, we're going to use bootstrapping with our decision trees. And so we're going to return to our rainbows and unicorns one last time. And then I'm hesitant to promise because I can't really remember, but I'm pretty sure this is the last time that we'll be back with our unicorns. All right, so let's say we have a sample of 4 observations here, and we're going to use bootstrap resampling. So we have one bootstrap sample, and then we do more and more. It could be however many we want. In this case, we're going to do 3. And the way that this is going to work is that we will then what's called bag these different models. And so bagging is short for bootstrap aggregating. So we're going to take our training data, we're going to resample with replacement, and then from each model, we're going to get predictions, and then a majority vote, quote unquote vote, will be like the final prediction for each observation. And so we'll look at, we're going to go into detail about what's actually happening here. So we have our sample up here on the top left, and we take multiple different resamples. So we have our first resample, second resample, third resample. For each one of these, we're going to create a decision tree model, and we get a fitted tree from each of these different resampled data sets. All right, and so if we have our training set, we have for each observation, whether it was truly a horse or a unicorn. And so we have this unicorn variable that's binary, either true or false. And then we also have the number of rainbows and the number of butterflies, which are the predictors in our model. And so for each of our resample data sets, we estimate that fitted tree object. And from each of those, we can estimate and get our predicted class for each observation. So you can see in this first model, we predicted that everyone was a unicorn, right? In the second model, we predicted that case 1, 2, and 4 were horses, and the third was a unicorn. And in the third model here from our third resample, we predicted that cases 1 and 2 were a horse, and cases 3 and 4 were a unicorn. And so then to aggregate these decisions, we take a majority vote, right? So in the case of the first observation, we had 2 votes for horse and 1 vote for unicorn. So we get a final vote of horse. The same for the second observation. We had 1 vote for unicorn, 2 vote for horse. The third observation had 3 votes for unicorn. So we get a unicorn is the final decision here. And then the last observation had 2 votes for unicorn, 1 for horse. So they also get a final vote of unicorn. Right? And from that, we can then do our metrics. And so you can see in our testing data set, which was the bottom half up here, the true values were horse, horse, unicorn, unicorn. And that was our final vote as well. Horse, horse, unicorn, unicorn. And so our metric says that all of these 4 were correct predictions. All right, and so that's how this bootstrap aggregating of decision trees or bagged decision trees is working. We're taking our training data, we're resampling it, fitting the decision tree to each of those resamples, and then aggregating across all of those different tree models to get our final prediction. All right, so another modeling axiom that we have is that there's going to be an inverse relationship between model accuracy and model interpretability. Some of these machine learning methods, especially the random forest, which we're about to talk about, can be very powerful and give you really accurate predictions, but it's very hard to interpret what that model is actually doing. So we'll look at some examples really quick before we break for lunch. So here is a decision tree that has been bootstrapped resample. So all of these points in the background here are our sample. And you can see the blue points are the points that were selected for this particular resample, and the larger points mean those ones were selected multiple times. The gray dots were those that were unselected. And so for each of these trees, we get, or for each of these different bootstrapped resamples, we get a slightly different decision tree. All right, so here's one example. A different bootstrap will give us a slightly different tree, and another different tree, and another different tree, and another one, just depending on what that sample is going to look like. And so eventually we end up with all of these different bootstrapped trees that are kind of a mess when they're all put together like this. But if we average all of those together, then we get this like really squiggly, funky looking line, right? And so this is going to be more accurate than any one individual tree, but you can see like it's very hard to interpret what this is actually doing. So like for a single decision tree, we can say like, okay, anywhere that is like anywhere that has like less than this unicorn, number of unicorns has this number of predicted rainbows, and greater has this number of predicted rainbows. But for the bagged tree, it's much harder to make that comparison, right? The squiggly line is not super interpretable. And for a larger sample, it can get even more accurate, but also more squiggly. So we have a bunch of different bootstrapped trees here for our large sample. And this results in a bagged tree or an average tree that looks something like this, right? So again, we're going to get very accurate predictions usually from this type of model, or I will not say we'll always get accurate predictions. This type of model is going to be very powerful. So like you'll probably get better predictions from like a random forest than you might from like a logistic regression model. But how good the predictions are is still going to be dependent on the data you give it. So if you're not giving it good predictor variables, you're still not going to get good predictions, right? So no amount of fancy modeling is going to make up for bad data, right? So garbage in, garbage out, that is still going to apply to all of these different models. All right, and so in the modeling world, these bagged trees are known as a random forest, right? So instead of one decision tree, you put a bunch of trees together, you get a forest. And so this is the random forest, right? And I know we are coming up on lunch, and this is probably a good a place as any to go ahead and pause. So we will stop here at random forests. And when we get back from lunch, we'll talk a lot about the random forest, how it works in R, how we can estimate those models, and how that is going to compare to our different tree specifications that we've already fit, that vanilla tree and the big tree model as well. All right, so we will come back at 1:30 p.m. Central Time. But everyone have a great lunch, and I will see you then. All right, welcome back from lunch. Hope everyone had a nice break. So before we broke for lunch, we were talking about how we could take multiple decision trees that were bootstrapped together and averaged or bagged in this case, and estimate that as one model, right? So we mentioned that this is going to be a random forest model. And so in tidy models, and specifically in the parsnip package that we've been using to specify models, we can specify a random forest using the rand forest function. And it takes a few arguments. One is mtry, which we'll talk about in just a little bit. Another argument is the number of trees. So in our last example, when we were looking at all of these different bootstrap trees that get aggregated together, the trees is specifying how many of those trees we want to estimate. And then min is again the same as it was before, which is the minimum node size that we will allow to split. And just as with a decision tree, random forest can be used for either regression problems or classification problems. So you can use a random forest for both and it will work. All right, so here again are the arguments that go into a random forest. mtry is the number of predictors that are seen at each node. So in our examples so far with decision trees, we've basically allowed all of the variables to be seen, all of our predictor variables. And then the model can decide, okay, if we split on this variable, that's going to give us the most information. But we can limit that. So we can say we only want to let the model see 4 variables at a time, right? And it'll randomly pick which 4 it gets to see. And this is a way to help prevent us from overfitting, right? So we're not always just going for the most informative split, right? Because that's going to be dependent on our sample. So we might want to have some way to limit like which variables we can split on. And so that's mtry. It's going to limit the number of predictors we can see at each node. And then again, the trees is the number of trees that are going to be in our forest, how many decision trees are going to get estimated. And then again, min n is the smallest node that we will allow. All right, so let's go ahead and fit a random forest model. So we're going to build a new model specification, and you can call that RF spec for random forest specification. And we're going to use that to learn an ensemble of classification trees on our training data. And we'll use the Ranger package as our engine. We're then going to compare the metrics from this random forest model to the 2 single tree models that we've estimated so far, the vanilla spec and the big tree spec. All right, and so after you fit the random forest model, compare the metrics that you get to the other 2 and see which one is giving you the best model performance. All right, so let's look at how we can fit this random forest model. So the first thing we're going to do is create our random forest model specification. And we'll do that with the rand forest function. And for now, we'll just accept the default arguments for that one. For our engine, we want to use the Ranger package. And here, because the random forest works for both regression and classification, we need to set our mode. So that's how we want to use classification for this, since we're predicting the remote status of the Stack Overflow data. So again, I'll set a random C just so that my random forest model reproduces. And so for our model, we can fit resamples. And here we're going to fit our random forest model specification. Again, we're going to use our same formula of predicting remote status from all other variables. And our resamples, we will use the Stack Overflow folds. And then to get our metrics, we'll take our fitted model and use the collect metrics function. So if we run that, it will fit our random forest model to each of the folds in our data. And we get an accuracy and an area under the curve of 0.64 and 0.7 respectively. Was everyone able to run their random forest and get something similar to this? It won't be exactly the same unless you set your random seed as well. Awesome, good. And so we can compare this to our other models. If we look at our comparison, so our vanilla decision tree had an ROC of about 0.66. Our big decision tree, which we knew was going to be a little bit overfit, was 0.59. And here the area under the curve for our random forest is up to 0.7. So you can see it is doing a little bit better job of predicting than our vanilla decision tree was. So let's talk more about this mtry parameter for the random forest. So mtry is, again, the number of predictors that are going to be randomly sampled at each split when creating the tree models. And so the default value for mtry is the square root of the total number of predictors you have, and then always rounded down. So that's what the floor function in R will do. It will always round it down for you. So that's the default, but we can change that and see what the effect is on our model if we allow a different number of predictors to be used. So let's go ahead and do that. We're going to create 4 more random forest model specifications. So it will look very similar to the code we just ran, except for these new 4 model specifications, we want to specify the mtry parameter. So we'll use parameters of 4, 8, 12, and 20. So go ahead and fit those 4 models and see which mtry is going to maximize the area under the ROC curve. All right, so let's make some more random forest models. So there are a couple ways that we can do this. One option is to make each model specification from scratch. So I could say my random forest with 4 mtry specification is going to be a rand forest with mtry equal to 4. Set the engine to Ranger and set the mode to classification. The other option I have is I can take our existing kind of vanilla random forest specification and just modify that. So I can say the random forest with 8 specification, go ahead and start with our plain RF spec, and then just set the args for that one to be mtry equals 8. And so if I run this first one, I can see that this is a random forest model with mtry equal to 4. And similarly, if I run this one, I see that I get a random forest model with mtry set to 8. So either one of these will work to specify all of our models. But I think this one is a little bit less typing, so I will do that. So I wanted 4, 8, 12, and 20. So change these to 12 and 20. And then I need to estimate these models. So I will fit resamples. This is going to be the RF4 specification. Again, our same formula and the same set of resamples. And when I estimate that, I want to collect the metrics. And I'll do the same thing for our other 3 models that we're estimating. So here we'll do the 8 spec, the 12 spec, and the 20 spec. All right, and so we can estimate all of these. I won't run them right now because it'll take a little bit of time. But we can look at the results for each. If you were able to run these, hopefully you get similar results. So for mtry equals 4, I got an ROC of about 0.7. For mtry equals 8, an ROC of about 0.696, so about 0.7 again. mtry 12, 0.69, and then mtry 20, a 0.68. And so we can plot this if we want to. Look at the accuracy and the ROC as the mtry increases. This looks like a very dramatic decline here, but again, the scale of our y-axis is only going from a little over 0.7 to a little under 0.68. So even though it looks like a very steep drop, all these models are performing pretty similarly to each other. We can see it is dropping a little bit as the number of predictors we allow in increases, which we might expect. As we allow more predictors in, we're increasing the chance that we are overfitting. All right, and so if you wanted to do like a true bagged random forest, so remember in our original decision trees, mtry was not something that we thought about. We just allowed all of the predictors in. And we can do that here too by setting mtry to the total number of predictors. And there's a shortcut function called .preds. And so what that means is just set mtry to the total number of predictors that we have in our data. And so we can call this our tree bag specification. So our truly bagged decision trees. And if we fit this, we get an ROC again of 0.68. So pretty similar to our other models. And so again, that .preds function is just the number of columns in the data set that are associated with predictor variables. All right, and so here is our comparison of all of the 4 models that we've estimated now at this point. So we had our kind of vanilla decision tree that just had those default decision tree arguments. We fit a big decision tree. We fit our random forest, and we did our bagged model, which is the random forest with mtry set to the total number of predictors in our model. All right, and so now we're going to talk a little bit more about how we can tweak the engine when we're specifying our parsnip model. So far, all we've done for setting the engine is define the package or for LM, the function that's going to be used to actually estimate our model. But we can provide additional arguments to the set engine function as well. Those go in the place of these 3 dots. And those 3 dots are used for optional arguments that get passed to the function in Ranger that's actually doing the model estimation. And so one of these that we can provide to Ranger is this importance argument. So when we fit a random forest, we don't get any sort of model parameters out of it, right? So for our linear model, like our linear regression, we can look at the model coefficients and see, okay, this like this predictor has a large impact on our predicted score. It has a very large parameter associated with it, but for the random forest, we don't really get that. And that's part of what we were talking about earlier, where the model is less interpretable, right? But we can look at importance. And so this is going to help us understand a little bit which predictors are having a big impact on the predictions that are being made by the model. And there are different types of importance you can calculate. For example, we can specify impurity. And I will just be honest, I am not a machine learning or a random forest expert. So I am not an expert by any means on like what these different types of importance are or how they differ from each other. I just know that they exist and can be used. So we'll look at a couple of different types of importance and how you can use them. But I will not be able to help explain the difference between them. So we can create a new random forest model specification. I've called this our importance specification because we're going to add variable importance to it. And so here I've set mtry equal to 4. Again, we set the engine to Ranger and add this importance equals impurity. And then we can fit this model the same way we always would, just with the fit function, but we are just using our importance specification. And now when we get our fit object, it gives us the same sort of information. We have our time it took the model to estimate, the call to Ranger that was actually used to estimate the model. And so now you can see the importance has been set to impurity in this function call. And we get some information about the model. So the total number of trees, our total sample size, the number of independent variables we had, what our mtry was. And again, we see that variable importance mode was set to impurity. And so once we have that, we can use the VIP package, which stands for variable importance plots, to view which variables are most important to our model. So in the VIP package, there's a VIP function that will plot these important scores that are returned in our parsnip model. So we give it an object, which in this case is going to be our fitted model. And then we tell it what geom we want to make this plot out of. So we can use points, we can use columns, we can use a box plot or a violin plot as well. So for example, we can say VIP for our importance fit object with geom equal to point, and we get a ggplot that shows us the most important predictors in our model. So we can see that salary is a very good predictor of whether someone is working remotely or not, followed by the years they've been coding on the job, the size of the company, career satisfaction, the country where they work, etc. So we don't get model parameters, but we do have a way to see which predictors are being the most influential in our model. All right, so let's play with this for a little bit. I want you all to make a new model specification called tree bag imp spec. So that's for a bagged tree with importance. And we want to fit a fully bagged classification tree model. So that means we want mtry set to the total number of predictors, and then set the variable importance mode to permutation. Right, so this is a slightly different form of variable importance. It's permutation instead of impurity. And then use the VIP function to look at the variable importance plot. All right, so we'll take a few minutes to work on that and see if we all got similar results. All right, so let's fit this model. All right, so first we need to make our model specification. So we wanted to call it tree bag imp spec. And this is, again, a random forest model. And we wanted to set the m try equal to the total number of predictors in our model. So again, we'll use that dot preds convenience function. We'll set our engine again to ranger with importance set to permutation. And finally, again, we will set our mode to classification. So then we fit our model. So tree bag imp specification. Our formula is the same. Remote predicted by everything else in our data. And for the data here, we can use the Stack Overflow training data, or we could use fit resamples. But actually, I take that back. We cannot use fit resamples. So fit resamples does not actually save the models that are estimated, right? So the purpose of fit resamples is to estimate model performance. So we're always just collecting metrics from it. So fit resamples will not save the model objects and therefore does not save the variable importance. So we can't use our bfold cross-validation. So when we would do variable importance is when we're fitting our final model on all of our training data. And that will give us, that will return the model object that we can pull variable importance from. And so there are like different times that we're splitting the data. So we've looked at the initial split function. We've looked at resampling techniques. And we'll look tomorrow when we do our final case study. We'll go through like a whole modeling pipeline from the beginning, which is that initial split function, to the very end. So we'll learn about a function called last fit that puts everything together. So hopefully it'll be a little more clear tomorrow how all these different pieces fit together. But for now, we can use the fit function, but use it on our training data, not our resamples. And so if we save this as our imp fit, we can estimate this model. And then finally, we can use VIP on our imp fit, and we'll get a variable importance plot that looks like this. So we have, again, salary, years, coding, company size, country. So even though we've used a different variable importance, we've used permutation instead of impurity, and we get similar results for what's important. Was everyone able to get this graph or a similar graph? I will take silence as a yes, but let me know if we need to go back and look at it more closely. All right, so that is ensembling, which again is taking many models and making one out of it. So we're taking all of those decision trees and bagging them together in one random forest model. So random forest is an ensembling technique. Does anyone have any final questions about model ensembling or anything we've talked about so far before we move into our next set of slides? Nope. All right. So let me pull those up. All right, so we're now going to talk about modeling workflows. So we've had a lot of different pieces in the Tidy Models ecosystem so far. And we're going to talk about how to start putting these all together so that we don't have to try and track all of the individual pieces separately. All right, so let's go ahead and start by opening up the workflows exercises. So again, in your exercises folder, we're now on number 12. I will also pull that up. We will run our setup chunk. All right. Okay, so what we're talking about now is data analysis as a pipeline, right? So it's not just a model, it's also how we manipulate the data, how we interpret our model output, how we measure model performance. It's all together in a single pipeline. However, just as with water pipelines, there's a threat of leakage, like your pipe can start leaking and cause a lot of damage in your house. In data analysis, there can be data leakage, right? And this has its own set of problems that we need to make sure we guard against. All right, and we'll talk about what data leakage is as well. All right, so a quick quiz thought experiment. So what is this set of code going to do? So we're starting with the AIMS data, which we saw yesterday. So again, this is the AIMS housing data, where it has the sale price of different houses that were sold. So we're starting with the AIMS data and we're adding a new variable. So we're using mutate, and the variable is called Z price. And that is going to be a Z score of the sale price, right? So taking the sale price minus the mean divided by the standard deviation. And that's our standardized Z score for the price. And then once we have that, we're creating a split object. So we're splitting this data into a training and a testing set. All right, and so if we look at what that data would look like, we have the sale price, and then we have the standardized Z-score for the price. And so what could go wrong with this type of workflow? If we take the mean and the standard deviation of the sale price, we transform all of the sale prices in AIMS to those standardized Z-scores, and then we split it and we train with our training set and we predict and we get metrics with our testing set. Does anyone see any potential problems? So the problem that I see is that our training data and our testing data are not independent anymore, right? They're not fully distinct from each other. We're using information from both the testing data and the training data to calculate that Z-score, which is then being used in the model. All right, and so that's what data leakage is. We have data from our test set leaking into our training data. And we don't want that because then we're not fully testing our model on new data, right? That data has influenced how the model is being trained. And so you might think, okay, we will split the data first, then calculate a z-score for the training data separately. So here, this z-score has not been influenced by our testing data. And then we can do the same thing for our testing data. We get that, we calculate a z-score, and then we fit our model and get predictions. Right? Does anyone have thoughts on what could go wrong with this sort of process? So the problem that we potentially run into is that these z-scores are going to mean different things, right? The mean of sale price in our training data is not going to be the same as the mean of our sale price in the testing data. So an observation that might have got a z-score of 1 here could get a z-score of 1.5 in the testing data, right? And so if the z-scores don't mean the same thing, just due to the characteristics of our random sample, then we're not going to get great predictions, right? So what we really want to do is we want to split our data. We want to transform the training set based on the mean and standard deviation of the sale price of the training set, train our model, and then transform the testing set using that same mean and standard deviation that we did from the training set, right? So this way we're calculating z-scores for both sets of data in the exact same way. We're using the same mean and the same standard deviation, but that mean and standard deviation that we're using are based only on the training set, right? And then we can predict the sale prices. So this is how we would prevent data leakage in this particular example. Is this making sense how the data can leak across the testing set and the training set and what we would want to do to try and avoid that? Yes, good. Awesome. All right, so just our definition of data leakage is when the data you're using to train the machine learning algorithm happens to have the information you're also trying to predict, right? So that's what we're trying to prevent. All right, and so our learner or our model is more than just the model, right? The machine learning or the pipeline that we're building is more than just the model. It's also how we're getting data into that model. And so our learner is only going to be as good as the data that we give it, and our data is only as good as the workflow that we set up. So our revised goal for machine learning is not to build models, it's to build reliable workflows that are going to generate accurate predictions for future data, right? So it's about more than just the model, it's about building a workflow that is going to help give us accurate predictions in a robust way that's preventing data leakage. Right, so we have I think I briefly mentioned this earlier. GIGO is garbage in, garbage out. So again, we have to give it good data and give it a good workflow in order to get good predictions out of our models. And so another way of thinking about this is that feature engineering, which we'll talk about maybe this afternoon. If we have time, we'll get started on that. If not, for sure, tomorrow morning. Feature engineering and modeling are two halves of a single predictive workflow. And so we've seen this a little bit. It's like when we were calculating the z-score just a few slides ago, like that is feature engineering. We're calculating a new feature from the data that we have. Right? And so we need both good feature engineering and good modeling in order to have a good workflow. All right, and so we saw this graph earlier. We have our old data that is used with our model to get a trained model. We then add new data to that trained model to get predictions, which then can be used to improve our model. But we're going to modify this a little bit. So we take our old data, we do some sort of pre-processing. We add that to our model. And then we do the same pre-processing to our new data and add that to our trained model. And in order to use the same pre-processing steps in both places, we're gonna, in a sense, we're gonna prep this pre-processing recipe, right? So we're gonna use the same pre-processing for both the old data and the new data, right? And so this is what becomes our workflow. It's this process of pre-processing and modeling on our old data, and then pre-processing and getting predictions from the trained model on our new data. Right, but it doesn't have to necessarily have pre-processing. Like we could just keep our data exactly as it is. That's what we've been doing so far the last 2 days. And we've just used our Stack Overflow and the Ames housing data as it comes. Or we could use a recipe. So recipes are what we're going to talk about with feature engineering. I think we'll have time to get started on that today. If not, we'll do it tomorrow morning. All right, and so we're going to put all of this together into a workflow. Like how do we keep that pre-processing and the modeling all together as one coherent pipeline? All right, so we are right up on a break. So why don't we go ahead and take 15 minutes. That will be 2:40 Central Time. We'll come back and we'll talk about how to actually create a workflow in R. All right, so 2:40 Central Time. All right, give me a thumbs up if you are back. Awesome. All right, so we're now going to switch to talking about how to actually create these workflows in R. And to do this, we're going to use the workflows package. And again, there is a chapter in the Tidy Modeling with R book about workflows and how to create them, but we're going to talk about them here as well. So within the workflow package, there is a workflow function that creates a workflow that you can add a model to and many more things as well. So if you have pre-processing steps, anything like that can be added to your workflow. For example, we can add a formula. So for our Ames data, we can say our formula for this workflow is we're going to predict sale price from the year the house sold, would be this example. And you would add this formula if you don't plan on doing your own pre-processing. So if you're just using the data as is, then you would use this add formula syntax. If you are doing pre-processing, we'll see how to add that to a workflow in just a little bit. You can also add a model. So we have here a linear model parsnip specification. So after we make that specification, we can add that model to our workflow. And then it'll just be included with everything else that's in the workflow as well. All right, and so let's return to our Ames housing data. So again, we're going to be looking at sale prices for houses. And let's try and build a workflow. So we are going to build a workflow that uses a linear model to predict sale price with the number of bedrooms that are above ground, the number of full baths, and the number of half baths in the Ames data. And we want to save this as BB workflow. So bedrooms and bathrooms workflow. All right, so let's take a few minutes to build this workflow. All right, so let's look at this workflow object. So the first thing that we need to do is make that linear model specification. So here we say we're going to a linear model, and we specify that with the linear reg function, and we set the engine to LM. And then to make our workflow, we use this workflow function to initialize the workflow. We add our formula, which again is predicting the sale price from the number of bedrooms and the number of bathrooms. And then we also add our model specification. And if we look at this BBWF object, we see that it is a workflow. It tells us that our preprocessor is just a formula, and it's going to fit a linear regression. Here in our preprocessor, it shows us what that formula is we specified. And again, it includes that model specification from the parsnip model that we made. All right, so it's keeping all of our pieces of our model together in this single workflow. And we can just sub this in to our fit and fit resamples functions that we've already been using. Right, so in our fit function, we would always specify, here's the model, here's the formula. Now, because the model and the formula are both in the workflow, we can just tell parsnip to fit the workflow to the data that we specify, right? So we no longer have to specify all these different pieces. It's all together in one workflow object. We can also update our workflow, just like we're able to update our model specifications. So if we have a workflow, we can use the update formula function to change our formula. So here we can say sale price just by the number of bedrooms. And then our preprocessor, you can see, has been changed to just include the bedrooms as a predictor variable. All right, so let's try fitting a model. So we want to predict sale price from everything else in the AIMS data, all other variables. And we want to use cross-validation to estimate the RMSE of our model, right? So we're going to create a new workflow by updating the BBWF workflow that we already made. So you use that update formula function to change the formula. We'll use vfold CV to create cross-validation sets from the AIMS trained data. We'll fit the workflow and then use collect metrics to get the estimated RMSE. So let's take a few minutes to work on that and then see if we all get similar answers. All right, so let's look at this workflow object. So to create our new workflow, we'll start with our old one, that BBWF object, and we just update the formula to say that we want to predict sale price from everything else in the data. And again, we use the period to indicate that. And then we can create our cross-validation fold. So we say v fold CV from the AIMS train data, and we want a 10-fold cross-validation. So we specify v equal to 10. And then we can use fit resamples. So we want to fit resamples to our new workflow, and the resamples we're going to use are those AIMS folds that we just created. And if you collect those metrics, you should get something similar to this. So you should have an RMSEA or RMSE somewhere around 41,000. Was everyone able to use fit resamples to fit their workflow? Great. Awesome. All right. And so we can also update our model in addition to updating the formula. So this is going to remove a model specification and then replace it with a new one. So let's give that a try. So now we're going to fill in the blanks for the code that's in your workbook. We're going to estimate a regression tree model that again is going to predict the sale price with everything else in the AIMS data using the AIMS fold. So again, we're going to use a decision tree now and see what RMSE we get from that. All right. So we can make our regression tree specification again with the decision tree function. And we set our engine to our part and the mode to regression since we have a continuous outcome now. And then we can update our workflow, right? And since the all workflow is already using all of the predictors, we can just update that workflow. And we update the model to now use our regression tree specification instead of the linear regression model specification. And we fit resamples to that new regression tree workflow on our same set of resamples, collect the metrics, and we get an RMSE of now about 41,500. So similar results for our regression tree to our just normal linear regression model. All right, and so we have one more exercise for this set of slides, and that is concerning the predictions from our model. So how can we get the predictions out from this if we wanted to? As I mentioned earlier, the fit resamples does not save the models by default, but we can make it save some more information than just the metrics. And so we can tell it to save the predictions, for example. And so there is some code in your notebook that does this. So go ahead and save the fitted object from the regression tree. If I remember correctly, it should be, yeah. So we will fit our workflow again, but this time with saving the predictions. So here, we're going to control the resamples and tell it to save the predictions. And then you can use the collect predictions function, just like we've been using the collect metrics function to look at the predictions from each of our models. So it'll take just a few minutes to get those predictions. All right. So again, if we look at how we can fit this, we use fit resamples again on our regression tree workflow and our same set of cross-validation folds. And this new control line is just telling the fit resamples function to save our predictions. And then we can look at those with collect predictions. And so we can see for fold 1, these were the rows that were held out as part of the testing set. And we can see the predicted price and also the true value of the sale price. So collect predictions will show you not only the prediction, but the observed value as well. And you'll have that for every fold in the data. So does anyone have any questions about workflows? No? All right, well, we will go ahead and start our next set of slides. We have about 20 minutes left today. And I think that will be good to give us a little bit of a head start for tomorrow, because we do have a lot that I want to cover in our last day. All right. Oops. We're a little bit frozen. See if it will load, maybe. Okay. All right, so we're going to talk now about feature engineering and how we can get more information out of the data that we have. All right, so let's go ahead and open the next set of exercises. That's going to be it's called recipes, number 13, and go ahead and run that setup chunk. I will do the same. And so we'll load some packages for us. All right. And so for feature engineering, we're going to be using the recipes package. So we're back to our food-based packages. We get a cupcake for recipes. And again, there's a chapter on feature engineering with the recipes package in the tidy modeling with our book. That's really good. All right, and so we're back to this pre-processing diagram we were looking at earlier, looking at workflows that use a recipe to inform the pre-processing for our models. And so this is another flow chart that we've seen before. So we have our original data that's going to get split into old data and new data. And that splitting happens with the rsample package. We can then apply pre-processing and modeling to our old data and our new data. So that's going to happen with the recipes and the parsnip package. Another package that we're going to talk about tomorrow is the tune package. That's going to be used to help us look at some parameters from our model that we can't estimate from the data. So for example, when we were playing with different values of mtry earlier, we can use the tune package to help us figure out what value is going to be best. And then finally, we use the yardstick package to calculate metrics and evaluate our models. All right, so has anyone heard of multicollinearity before? Yes, good. So multicollinearity is when our predictor variables are going to be very strongly correlated with each other. And that's going to impair our linear models. So one way that we can get around multicollinearity is by doing a principal components analysis. All right, so this is going to transform our variables into components that most concisely capture the variation. And so our goal is going to be to fit a linear model to the main principal components of the AIMS data. So instead of just using all of the variables in that data set, we want to pull out just the main components and use those as our predictors. All right, to do this, we're going to build a recipe. So you start the recipe with the recipe function. You define the variables that are involved, and then you describe your pre-processing step by step, as that's called prepping the recipe. So recipe is going to create a recipe for a set of variables. So here we start our recipe with a formula, and we say that the sale price is going to be predicted by all of the other variables, and we specify that the data we're using for that is the AIMS data. And then we use a series of step functions. And these are going to add a single transformation to our recipe. And the transformations are then replayed in the order they're specified when the recipe is run on the data. So for example, here we've used step novel, and that step gets applied to all of our nominal or categorical predictors. And step ZV, which ZV stands for zero variance. So it's going to remove any variable that has zero variance. So it's just a constant. And we're going to talk about more of these in detail, but this is just an example of what a recipe will look like. So there are a ton of different steps that can be applied. This link lists a lot of them on the recipe website. So if you scroll down to the step functions, there's a bunch for imputation if you have missing data. There are step functions for individual transformations. So there are a lot of different step functions that you might want to apply to your recipe. And there are also selector variables. So we saw this earlier. You can use these shortcuts to, for example, apply a step to all of the categorical predictors or all of your predictors without having to specify each one individually. So there are the selectors that are available. You can use all predictors, all outcomes if you want to apply something to your variable as being predicted. You can apply to all numeric predictors, all categorical predictors. And you can also use some select helpers from the dplyr package. So you could apply a recipe step to, for example, all of the variables that start with a specific string. So all the predictors that start with lot underscore would have a step applied to it. And you can combine selectors also. For example, we can apply this step to all categorical variables except the outcomes. We don't want the outcomes to be included in this step. So you can put multiple selectors together. So a pop quiz, how does a recipe know what is a predictor and what is an outcome? So this is going to come from how our recipe is initiated. So when we start our recipe, remember we give it a formula. We said our recipe is going to start with sale price predicted by everything else. And that is how it's going to know. The formula is going to indicate to the recipe what is an outcome and what is a predictor. Okay. And the second question now is, how does the recipe know what is numeric and what is categorical? This is going to be determined by the template data that we give it. So here we're giving it a real data set, but recipe is not actually applying this data to the recipe, right? It's only being used to catalog the names of the variables and the types of each variable. So that way, when it builds the recipe, it knows, okay, these are the variables I need to do these steps to when it's actually time to pre-process the data. All right. So for us, since we're interested in doing a principal components analysis of the AIMS data, principal components requires our variables to be centered and scaled. So what does that mean? That is going to mean that our variables need to be standardized or a z-score. So this is an example we looked at earlier on how z-scores could go wrong with our AIMS data. And here we're going to look at how to do it in a safe way that prevents data leakage with the recipes package. So we can use step center. So we start with our recipe that has our formula and our data. And first we want to center all of our numeric variables. And then we can scale, again, all of our numeric variables. And so this is going to divide by the standard deviation. And so now we have a recipe that's going to center and scale all of the numeric variables in our data set. And so why do we need to train a recipe, right? And so we talked about this earlier. If we are scaling a new data point, we need to know what mean to use and what standard deviation to use when we're calculating that standardized z-score, right? So we need to train our recipe so that it knows exactly how to transform any new data set that's fed to it. So to modify our flowchart a little bit, we have our recipe that is used for our old data and goes to the model. And then we use the prepped recipe on our new data and the trained model. So our recipe might say center all numeric variables and scale all numeric variables. And the prepped recipe is going to be specific about subtract 2000 from year, divide year by 15. Subtract 2 from whatever the next numerical variable is, divide by whatever that standard deviation should be, right? So the recipe is a set of steps. The prepped recipe is actually what's happening at each point. And so the functions that will do this for us are prep and bake. Recipes is very into the food analogies. So prep is going to train a recipe, and then bake will apply that recipe to a new data set. Excuse me. But we won't actually need to do the prepping and the baking ourselves. The fit function, so fit and fit resamples, will automatically take care of this for us as part of the workflow. All right, so here's just an overview of what this recipes package is doing. We start with all of our variables in like a pantry. We specify what those variables are in our model, again with the formula. We create our recipe by defining the pre-processing steps, and then we provide the data set to train it, and we can apply the pre-processing to new data. And so if we look at what this might do, we can have our recipe, we train it on the training data, and then we can apply that recipe to our test data. And we get back our test data, but all of the numeric variables have been centered and scaled. So if you compare this data to the original AIMS data, you'll see that these values are now on a z-score metric. All right, so what happens, or I guess your quiz, is if we have a factor variable that has 6 levels, what is it called when we put it into this sort of format, if you've ever done categorical variables in a regression model before? So this is what is known as dummy coding or dummy variables. where instead of one variable for the factors, we create a new variable that indicates either 1 for what type of, in this case, roof style it is, or 0 if it's not that style of roof. And this is done automatically in the LM package. Like if you try and fit a linear regression model with a categorical predictor, it will automatically dummy code for you. But we want to control how that process is happening. And so there is a recipe step called step dummy that will convert all of our categorical variables into dummy variables, which are then numeric and suitable for any type of linear algebra that can't deal with categorical variables. But I will also note that you do not need to make dummy variables for decision trees or random forests. They are perfectly capable of handling categorical variables as they are. All right, so we'll get through just a few more slides this afternoon. So let's think about the modeling process and dummy variables. Like what would happen if there were no homes with shed roofs in our training data? Would the model then have a coefficient for a shed roof? And the answer is no. Like if there's no shed roofs in our data set that trains the model, then we won't get a coefficient back. And so then what happens if the test data does have a shed roof? How do we make a prediction for a roof that doesn't have a coefficient in our model? We get an error and it breaks. So we need a way to handle this type of situation. This is step novel that we saw earlier. And what step novel does is it just adds like a catch-all level to any factor for any new values that pop up. So if there are values in your testing set that were not in your training set, R is going to basically intelligently predict the new levels for you. So that way you don't get an error if new values show up. And so again, we can apply step novel to all of our categorical variables and then create a step dummy. But again, the order here matters. So you want to make sure that all of the levels have been created for your categorical variables before you create your dummy variables. All right, and so what would happen if you try and scale a variable that doesn't vary? So if we try and divide by the standard deviation of a variable that has no variance, again, we'll get an error because we're dividing by 0. If a variable doesn't vary, its variance is 0, standard deviation is 0. So we divide by 0 and get an error. And so this is where step ZV comes in. It will basically get rid of any variables that have 0 variance. And that's fine because if a variable doesn't have any variance, it's not giving us any information for our predictions, right? Because every observation has the same value. And finally, our last thing that we'll talk about today is what step function is going to do a principal component analysis for us. So there is a function called step PCA, which is documented on the recipes website, which will take all of your predictors and perform a principal components analysis on our data. And so we can use step PCA and say we want to apply this to all of our numeric variables. And then we tell it how many components we want to extract, right? So here we specified 5, but you could specify a different number of components if you wanted to. And we'll also look, when we talk about the tune package tomorrow, we can tune not only our models, but we can tune recipes as well. So we'll figure out how to easily and efficiently find what the best value of the components might be. All right, and so that is an introduction to how we're going to build recipes and how we're going to start to build this principal components analysis model. We'll go ahead and stop there. If you really want to get a jump on it, you can try to build this first recipe tonight if you want, but this is where we'll pick up tomorrow. We'll start by trying to build our first recipe in the morning. So I will see you all back at 9 o'clock Central Time tomorrow morning, and that will be our last day of this workshop. So thank you all for hanging in there.